Okay, let us come to this next theorem. Let n be a normal subgroup of G and H is just a subgroup of G. Okay, n here is normal in G and H is just a subgroup of G. Then what we need to prove is that H intersection n must be a normal subgroup in H. Number 2, Hn is a subgroup of G and n must be a normal subgroup of Hn. So let us prove the first one. To prove that H intersection n is a normal subgroup of H. Now we know that H intersection n is always contained in H. Also, H intersection n is always a subset of n. So now what we need to show is that, so this implies that this one is a subset of this. I need to show that it is a subgroup in H and it is also normal in H. So for that I need to prove first that H intersection n is a subgroup of H. So let us apply this result. In order to show that this subgroup is this set is a subgroup, I need to take any two elements of this set. A belongs to H. Then if I can show AB inverse belongs to H, then I can conclude that H is a subgroup of G. Here instead of H, it is H intersection n. So now here let us take, let AB belongs to H intersection n. This will imply that A belongs to H and B belongs to H by definition of subset. If A and B belongs to the intersection of two set, then it must belong to both of those two sets. So it implies here A belongs to H and B belongs to H. Belongs to H, and at the same time A belongs to N, B belongs to N. So now here A belongs to H, B belongs to H, it implies that AB inverse belongs to H. This is true because H is a subgroup of G. Similarly, N being a subgroup of G, so A belongs to H, B belongs to H will implies that AB inverse belongs to N. So now you can see that AB inverse belongs to H and at the same time belongs to N. So it implies that AB inverse belongs to H intersection N. So which means that it satisfies this definition of this theorem on subgroups. So it implies that H intersection N is a subgroup of G. Now next I need to show that it is normal in H. So for that one I have to use this definition of normal subgroup. That is this one. If I can take an element say K in H intersection N and X in G, then in this one is in H. So I need to take H in H and then an element which belong to their intersection, and if I can show that that element X inverse belongs to this set, then it will be a normal subgroup of G. So for this one you take, let H belong to H intersection N and X belongs to H. Now X inverse, this is equal to what? This will it belongs to N or not? Now X inverse, H is in H intersection N and X belongs to H. So it will imply that X inverse will belongs to H. Why? Because H is a subgroup of G. So H is in H, X is in H, X inverse will naturally belongs to H. And what about X inverse? Will it belong to N or not? Here H is an element of N also because H belongs to their intersection. So H belongs to N will imply that for every X in G, X inverse will belongs to N. Why? Because N is a normal subgroup of G. So it implies that X inverse also belongs to N. So from these two it implies that X inverse belongs to their intersection. So which means that H intersection N is a normal subgroup of G. So this proved the first part. Now let us come to the second part, that is Hn is a subgroup of G. So Hn, what is Hn? By definition of product of two subgroups, it is defined as Hn such that H belongs to H, N belong to N. Now take any two elements of Hn. It is H1 N1 and H2 N2 belongs to Hn, where H1 H2 are elements of H and the second one N1 N2 belongs to N. Now let us show that if I can show that h1n1 into h2n2 the whole inverse belongs to hn, then I can conclude that this one is a subgroup of G. Using again this theorem, if A and B belongs to H, if and only if AB inverse also belongs to H. So this acts as A, this acts as B. So now this is equal to h1n1. Now h2n2 the whole inverse is equal to n2 inverse h2 inverse. This is by property of a group. Now you introduce h1, h2 inverse h2, n1, n2 inverse h2 inverse. That means in between h1 and n1 here, you introduce h2 inverse h2 because h2 inverse h2 gives you E and h1E is same as H. So by that property, we can introduce this h2 inverse h2 here. And this is called to h1, h2 inverse. Combine this first two together and the last four together. It will be h2, n1, n2 inverse into h2 inverse. So this is equal to 1. Now h1 is an element of H, h2 is an element of H. So h1, h2 inverse belongs to H because H is a subgroup of G. So this element belongs to H. Now what about the second one? That is the elements inside the bracket. H2 into n1, n2 inverse, h2 inverse. Will it belongs to N or not? Now n1, n2 inverse is an element of N. Why? Because n1, n2 belongs to N and N is a subgroup. So n1, n2 inverse belongs to N. So this middle element belongs to N. But what is given in N? What is the extra condition for N? N is given to be a normal subgroup of G. So if it is a normal subgroup of G, so for every H2 in G, H2 belongs to G because H is a subset of G. As H2 belongs to H, it will imply that H2 also belongs to G because H is a subset of G. So it is of the form X into N1, N2 inverse, X inverse. And this by definition of normal subgroup, it must belongs to N. Why? Because N is a normal subgroup of G. So it implies that the first element belongs to H and that the second one belongs to N. Then the whole thing will belong to Hn. So this implies that H1 N1 into H2 N2, the whole inverse belongs to NH. And by the statement of this theorem, we can conclude that Hn is a subgroup of G. Hn is a subgroup of H. Hn is a subgroup of G. Now the last one, this one. N is a normal subgroup of Hn. So I need to show that N is a normal subgroup of Hn. So for this one, first I need to show that N must be a subgroup of Hn. And secondly, I need to show that N must be normal in Hn. So we know that any element of N can be expressed as N is called En because E is the identity element in G. So En is same as N. And so as Ex is called to X for every X belong to G. So in particular for every N belong to N as N is a subset of G. So that's why we can express every N in N as En. So this implies that every N belong to N also belong to Hn because what are the elements of Hn? Hn contain these elements in the form small h into small n such that h belongs to H and n belong to N. So in particular, we know that E is a common element that belongs to H and N also. So you can see from the expression here that every element of N can be expressed as a product of an element of H and also an element of N. So this implies that N is a subset of, N is a subset of Hn. And since N we know that it is a subgroup of G, so it implies that N must be a subgroup in Hn because Hn is a subset of G. So this proves that N is a subgroup of Hn. Now let us show that N is normal in Hn. So for this one you take let N belongs to N and H1 N1 belongs to Hn. If I can show that H1 N1 N into H1 N1 the whole inverse belongs to N, then I can conclude that N is a normal subgroup of Hns. That is of the form X N X inverse, okay, where X here is H1 N1. So let us prove now h1 n1 n into h1 n1 the whole inverse is equal to what? It is h1 n1 n, then h1 n1 the whole inverse is equal to n1 inverse, then h1 inverse. So this is equal to h1, then combine these three elements which are in the middle, n1 n, n1 inverse into h1 inverse. Now these three elements, n1 n, n1 inverse, this belongs to n, because n belongs to n, n1 belongs to n, so n1 inverse also belongs to n, as n is a subgroup. So it implies that n1 n1 n into n1 inverse also belongs to n. So this belongs to n, and this is h1 which is an element of h. So it implies that it is of the form xn x inverse, where x here is h1, x inverse is this h1 inverse. So it is of this form. So as n is a normal subgroup of G, because this is given, n is a normal subgroup of G, so this whole thing will belongs to, that means this whole thing will belongs to n. So this implies that h1 n1 into n into h1 n1 the whole inverse belongs to n, which means that as this element x is an element of hn, so it implies that n is normal in hn. I hope it is clear now. You go through it. In case if it is not clear, then you please let me know.